as we said, digital modulations are much more popular than analog modulation. One of the most popular digital modulation technology that has been used since the first generation optical communication system is what is called as intensity modulation. Okay. Intensity modulation of the digital data. Okay. As we know, digital data is an abstract term. It comes as a sequence of zeros and ones, but these zeros and ones, they themselves cannot be applied to a modulator. I cannot take a modulator and say 0, I will not get anything. I can't take a modulator and say 1, I will not get anything. I have to convert these zeros and ones into appropriate voltage values. Okay. So, let us say for 0 I will use some u0 of t, and for 1 I will say u1 of t. This how exactly we do go from 0 1 to u0 of t and u1 of t is a subject of line coding that we will take up later. But now let us simply recall our transfer characteristic of the Mach Zehnder modulator and see if I can perform this digital modulation. Okay. What I would like to do in this digital modulation is that when I get an input 0, I should pick a value of u0 of t such that the output power will be equal to 0, or it should be very, very small. When I get a bit 1, this bit 1 has to be mapped to output power equal to 1, that is to the maximum operating point of the Mach Zehnder modulator. So, you have to switch between minimum transmission point or the 0 point of the modulator to the maximum transmission point, which would be at this stage, right. So, you have to switch between these two values as and when I get a sequence of zeros and ones. Okay. So, I have to choose the values of u0 of t such that for bit 0 I get the output power equal to 0. I have to choose u1 of t such that for the bit 1, which is mapped to u1 of t, the output power should be equal to 1. From the transfer characteristic, it is very, very simple and obvious what these values should be. At least there, of course, there are an infinite number of choices because the modulator transfer characteristic is periodic, but over this one period from minus v pi to plus v pi or from minus 2 v pi to plus 2 v pi, the choices are fairly simple. How do I obtain 0 transmission point? I have to choose u0 of t as v pi, correct. If I choose v pi, then if I map u0 of t, or if I take u0 of t is equal to v pi, whenever this u0 of t is applied, which is equivalent of applying v pi, then I will be at the 0 operating point, and this would represent the bit 0, right. So, bit 0 comes in, that 0 means you have to convert that 0 into v pi. Okay. So, I get a 0 operating point. So, my 0 bit is located here. Okay. This is a 0 bit, not the output power, this is a 0 bit. Similarly, whenever, so if I want to operate at the maximum transmission point, I have to choose either u1 of t as 0, or I have to choose that one to be as 2 v pi, because at 2 v pi the power transfer characteristic would be going to its maximum, right. So, the power characteristic would be going to its maximum. So, either I choose 0 or I choose 2 v pi. Okay. So, this is 2 v pi. So, this is 2 v pi, this is v pi, this is minus v pi, and this fellow is minus 2 v pi. So, if I choose 2 v pi, then I will be operating in the maximum transmission point and my output would be equal to 1. So, this would be my 1 bit. Okay. So, if I have a sequence of 0 1 0 1, then this sequence has to be converted into the appropriate u0 of t and u1 of t. What would that conversion be? Send v pi, when you get 1 you send 2 v pi, you send v pi, you send 2 v pi. Okay. In time, of course, it would go like this. So, this is my 0, sorry, this is my 1 0 1 0 1 input sequence. Corresponding to this is in time, and the corresponding analog signal, of course, this has to be an analog signal eventually. This is the digital signal, 0 1 0 1 is the digital sequence or digital signal, but this has to be converted into a waveform in order to apply to a Mach Zehnder modulator. This would form the analog signal, but the modulation is happening digitally. Okay. So, the signal corresponding to this, or the waveform corresponding to this bit sequence, would be for a 0 you put v pi, and for 1 you put 2 v pi, right. So, this would be the corresponding sequence. Okay. This would be function of time. The duration of 1 or 0 is called as the bit duration. So, the duration of 0 or 1 is called as the bit duration. In this case, each bit or each pulse of duration TB carries 1 bit of information. So, the bit rate, the rate at which we are transmitting these bits is equal to 1 by TB. This is sometimes written as RB. RB denotes the bit rate. In each time window of TB, I am sending one pulse, and each such pulse, right. So, each pulse would carry 1 bit. So, therefore, the bit rate of this intensity modulation or on off keying. Why is this called on off keying? Well, when you are, since you are moving between the on point of the Mach center modulator and you are transitioning from on to the off point of the Mach center modulator, this is called as on off keying. So, it is kind of operating like a key. So, whenever you get a 0, you go to the minimum transmission point, when you get 1, you go to the maximum transmission point. So, this is how you can perform intensity modulation of digital data or the on off keying. This is a popular modulation technology that has been used up to 10 Gbps optical communication systems. It has also been used for 40 Gbps, although beyond this using on off keying is not advisable, because the efficiency of the modulation, which is measured as the number of bits that you can send for a given bandwidth, bits per hertz, is very small. In fact, it is the smallest possible for this intensity modulation signal. So, for this on off keying. Okay. Let us now go from this complicated analog, amplitude modulation to a slightly simpler modulation, that of the phase modulation. Okay. Because for the phase modulation, the physical or the functional layer should tell you that if I have my carrier C of t, which would essentially be a sinusoidal carrier, and if I drive this modulator, phase modulator, with signal m of t, which is the message signal, what should I get? Well, I can't just write C of t into m of t or do anything. I have to assume what C of t is. So, let us assume that C of t is some square root Ps cos omega st. So, if I assume that the carrier is square root Ps cos omega st and m of t is the message signal that I am applying, then the output of this would be square root Ps cos omega st plus some constant kpm. This Pm stands for phase modulation times m of t. This is the sinusoidal carrier whose phase is being modulated or changed according to this m of t. This is the phase modulator functional relationship. Can we now look at what is the functional relationship for the phase modulator in the optical domain that we talked about? Well, in the phase modulator, what we had was an input signal u of t, which of course would be equivalent of having m of t here, and then to this phase modulator the input was E in of t coming from the laser. This laser output was square root Ps, and in the real case it would be cos omega st, that is the real expression would be cos omega st, but the complex expression would tell you that this would be e to the power j omega st. For this phase modulator, the output electric field would be equal to input electric field, which is square root Ps e to the power j omega st, and because you are sending in this u of t, your additional term that comes in because of u of t would be e to the power j pi u of t divided by v pi. But if you understand that pi by v pi with whatever the input voltage that you are going to get with u of t, the peak value of that u of t can be taken to be some kpm, then you see that these two relationships are exactly equivalent. One of course written in terms of cos omega st, but all that you are saying here is nothing but the complex representation would be e to the power j omega st e to the power j kpm m of t, right. If you identify u of t with m of t, kpm with pi by v pi, then your phase modulator has exactly the same functional relationship as a phase modulator that you would expect from your, or you would have studied from your earlier courses. So, you expect phase modulator to perform its job by changing the phase of the carrier, and that is precisely what this optical phase modulator is doing. So, optical phase modulator has exactly same phase relationship, and you can now do analog modulation if your u of t happens to be an analog signal. For the case of sinusoidal phase modulation, you can take u of t to be some peak value u a c, cos of omega m t, and then you can see that the spectrum will have these Bessel functions, it will have sidebands which are infinite number and so on. So, you can recall all these ideas about phase modulating in the analog domain. So, analog phase modulation. So, that is I would not be discussing that one, but rather let us look at what we can do in terms of digital phase modulation. Okay. What do we mean by digital phase modulation? Let us consider the simplest case of what is called as binary phase shift keying. This is abbreviated normally as binary or abbreviated normally as BPSK. PSK stands for phase shift keying, B stands for binary phase shift keying. What is the point of a binary phase shift keying? Well, if I get a 0, I would like this 0 bit, this is actually 0 bit, right. This 0 bit be represented as phase phi 1. If I get a bit 1 at the input, I would like this to be represented as phase phi 2. How can I do that in terms of the optical phase modulator? Well, what is the phase that you want? Let us suppose that phi 1 happens to be equal to 0 and phi 2 must be equal to pi. These are two widely separated phases. So, it would be natural to assume that you can map 0 bit to 0 phase and 1 bit to pi, or you can turn it around, does not really matter, whichever that you take, that is up to you. The convention you can follow with either 0 being pi and 1 being 0. Okay. So, let us try with this constellation, later we can switch it if we think that this is not a very nice representation. Okay. When I have phi 1 equal to 0, what should my u1 of t should be chosen such that I get no phase shift? I can choose 0 or I can choose 2 v pi. If I want to get a phase shift of pi, what should I choose? I should choose u2 of t, which is the signal corresponding to phase phi 2, which then corresponds to bit 1. I should choose this one to be v pi, correct. So, if I alternate between 2 v pi and v pi, I am changing the phase of the laser light, that is laser light which is given as the input to the optical phase modulator. I am changing the phase of that light wave to go between 0 to pi. Let us look at this. Well, the output electric field here would be square root Ps e to the power j omega st and then e to the power j 0 or j 2 v pi. So, 0 into pi divided by v pi, this is nothing but 1 and this is equal to square root Ps e to the power j omega st. So, this is exactly what you have transmitted at the input. So, this E out is equal to E in with no phase difference. Okay. When you have u2 is equal to v pi, so this was the case when u1 of t is equal to 0. If you have u2 is equal to v pi, then in this case the output electric field will be given by square root of Ps exponential j omega st e to the power j pi v pi divided by v pi, but this v pi and v pi will cancel and e to the power j pi I know is equal to minus 1. So, I get minus square root of Ps e to the power j omega st. Okay. So, I have obtained binary phase shift keying. If you were to draw some waveforms to indicate how it would look, let us assume that I am transmitting this particular sequence. This is 1, this is 0, this is 1, 1 and 0. Okay. Correspondingly to this one, u1 of t will be 0 and for 1 you need to have v pi. Okay. So, the corresponding values here would be 0 voltage, v pi voltage, 0 voltage and then v pi 2 times, and this one would be again 0 at the last sequence. How would the waveforms look? Well, corresponding to 0 I should have square root Ps e to the power j omega st, then I should have minus square root Ps e to the power j omega st, then I should have square root Ps e to the power j omega st. Now, I should have minus square root Ps e to the power j omega st twice, right. So, I should have this particular sequence and then finally, I should close it up by having square root Ps e to the power j omega st. If I were to graph this, these are complex exponential terms, obviously I cannot graph them like this. What I have to do is to take the real part of each of this. Okay. So, I have to take the real part of each of this and then plot it. So, I have, let us say this is my time axis and these are my boundaries which I am considering. So, this would be a high frequency sinusoidal signal, which we will say take it to be a cosine signal, right. So, this would be a cosine signal and you would come at this point. So, let us see if I have gotten the number of terms correctly. So, I have 1, I have 2, then I should actually have one more here, because the number of cycles here should be an integral multiple. Okay. So, the number of cycles here must be an integral multiple. So, I have to be little careful while sketching. So, let me assume for simplicity that I have only one sketch here. So, I have like this. Okay. Please note that this would not be the carrier waveform. The carrier waveform will actually be like multiple such this one, because the frequency has to be very large. I am showing a very small frequency just for clarification, just to clarify the diagram here, but you should remember that this would actually be the carrier which is oscillating heavily. And what is the phase here? The phase is 0. Here the phase should become pi, which means that I cannot start a cosine omega st, I have to start a minus cosine omega st. So, I should actually have this particular waveform, right. Now, what happens at this particular junction where the bit the phase is going from 0 to pi? What should happen is there is a discontinuity in this phase. Okay. There is a discontinuity in this phase. Also, I have changed the amplitudes, but this have to be of the same amplitude. You can forget that amplitude part, I mean you can forgive that amplitude part. So, what is happening is as the phase changes from 0 to pi, there is a discontinuity at the boundary. What should be the next waveform? Well, I should have, I have done square root Ps e power j omega st, I have done this one. Now, I should again get square root Ps omega st, which would be a signal that would look like this, right. It would be a signal which is a cosine waveform. Then I should have a minus square root thing. Again I am seeing two phase discontinuities over here. So, whenever there is a phase change, there would be a phase discontinuity. Okay. This thing you have to keep in mind. This waveform that you have is again analog, you can see that things are changing except at the discontinuous boundaries. So, how can I call this as digital modulation? Well, it turns out that what you are interested is not in this amplitude variations, but rather in the phase, and when you perform the appropriate phase detection on this waveform, you will see that you will be extracting the phases 0, pi, 0, pi, pi, 0, which are then mapped actually to bit 0, 1, 0, 1, 1 and 0. So, although the modulation is digital, the final waveform that will be transmitted over the fiber is actually an analog waveform. Okay. So, this completes our understanding of BPSK and phase modulation. Of course, we will revisit all these in much more detail when we take up higher order modulation formats. Before leaving the subject of BPSK, let me introduce you to one figure in which we normally think of when we say BPSK, or this type of we represent BPSK. This figure represents what is called as the in phase and quadrature components. It is a plane in which the x axis is in phase component and the y axis is quadrature component. I will explain to you what in phase and quadrature is shortly or in the next module, but in phase simply means that it is the part of cosine omega st, whatever the component that gets multiplied to cosine omega st is the in phase component, whatever component that gets multiplied to sine omega st is called as the quadrature component, sometimes called as cosine component and sine component. The point about cos omega st and sine omega st is that they are orthogonal to each other. Okay. We will discuss what orthogonality of two waveforms mean. I mean, we are used to seeing orthogonality of two vectors, but later we will see that signals themselves can be considered as vectors. So, this cosine omega st and sine omega st can be considered as vectors in some sense, okay, which we will talk about, and in that case these two are orthogonal or perpendicular to each of them. Now, if you look at this expression that we have obtained for the binary phase modulation, what you will see is that the waveforms are consistently given by square root Ps cos omega st or minus square root Ps cos omega st. So, on one side which is representing bit 0 and bit 1, you have square root ps cos omega st. Since this portion is already talking about cos omega st, you can mark off a point whose distance would be square root ps. Okay. So, this would be square root ps, and you can think of this as this signal vector which lies entirely on the I or the in phase line. Okay. How about representing this minus square root ps? Well, you can represent minus square root ps by a point which is at minus square root ps itself. Okay. This is the 0 at minus square root ps. This would correspond to bit 0 and this corresponds to bit 1. If you are not happy about this constellation representation, you can write this as 1, write this as 0. All you are writing here are the bits, and the corresponding phase values are 0 or pi, and the corresponding amplitudes are square root ps or minus square root ps. This figure is incidentally called as a constellation. At this point we have constellation with only 2 points. Later we will see that you can modulate not only on the cosine omega st component, but also on the sine omega st component, and you can mix both of them. You can multiplex both of them in what is called as the quadrature carrier multiplexing, or the in phase and quadrature components are both getting modulated, and you will get quadrature amplitude modulation, because both amplitude as well as phase are being modulated, and this modulation can be represented graphically by this constellation diagram. Now, how do we actually realize this IQ modulation? Can we do IQ modulation in the optical domain? Well, it can be done by using what is called as the IQ modulator. We will talk about what IQ in the next module later, but for now, since we are talking about the modulator parts of the optical transmitter, let us finish by looking at IQ modulation. What is the structure of an IQ modulation? It will look little intimidating at first. You have the source coming in as E in of t, and then it splits into 2 portions. So far no surprises. What I should get here is E in by root 2, what I should get here is E in by root 2. Now, I put one Mach Zehnder modulator here, drive this one with a voltage which would be the difference voltage to the Mach Zehnder modulator. I call this as Ui of t, and also I drive this second modulator, second MZM which I put with Uq of t. So, this I stands for in phase voltage, Q stands for the quadrature drive voltage. Okay. Now, before I give this to the Mach Zehnder modulator, what I do is I will put this through a phase modulator. Okay, I will put this through a phase modulator. So, let me write down my phase modulator here. This phase modulator produces a pi by 2 phase shift. Okay. How can I produce a pi by 2 phase shift? All I have to do is take this phase modulator, which let us call this as PM, and then supply a constant voltage of V pi by 2. So, as long as you hold it constant to a value of V pi by 2, you can supply this and make the phase modulator produce a pi by 2 phase shift. Once you get the Mach Zehnder modulated outputs here, you can then combine to form the electric field output E out of t. If you of course look at what the Mach Zehnder modulated construction is, you know that this itself is an interferometer, correct. If we want to describe the relationship E out of t, I need to know what is the electric field here. This electric field is nothing but E in by root 2, E in of t by root 2 times cos pi Ui of t divided by 2 V pi. Let us assume that both modulators have the same value of V pi. In fact, we will assume that even the phase modulator has the same value of V pi. What would be the electric field here? The electric field here will be J times E in by root 2. Why should there be a J? This indicates 90-degree phase shift. Okay. So, this is J E in of t by root 2. The electric field here will be J by root 2 E in of t cos of pi Uq of t divided by 2 V pi. So, that sum of these two after multiplying by root 2 will be the electric field output E out of t. So, E out of t is equal to half E in of t, which is a constant, I am taking this out. I get cos of pi Ui of t divided by 2 V pi plus j cos pi Uq of t divided by 2 V pi. Okay. If I can somehow remove this cosine by going back to the same kind of biasing that we did for the amplitude modulation, I can remove this cos and forget about the minus signs that I am going to get, and take this pi by 2 v pi as some constant, pi by 2 v pi as constant, put everything into a constant thing. What I get is some constant times E in of t, which would be my carrier, okay, E in of t times u I of t plus j u q of t. So, this would be the IQ modulator electric field. We will discuss more about IQ modulator after we introduce IQ terminology in the next module. Thank you.